Okay, so I have started the recording. Welcome you all to 7th session. Today, our focus is going to be how the pipeline is implemented in a MIPS processor. Okay, we have been seeing a pipeline stages of MIPS processor, which is a RISC family of processors. It's a 32-bit processor, similar like ARM, but little different. I will show you there are differences there. The pipeline structure, how does it look like inside a MIPS? So what I'm going to show you is a simplest design, and actual design will be much more complex. And then we will add a little bit complexity to the design as we proceed. So today we will cover a couple of things. One is about studying about the pipeline design and then running through two instructions into the pipeline. Then I will talk about a new topic, which is about pipeline hazards. Okay. So let me start. So we are going to take our familiar instruction, add R1, R2, R3. This is the pipeline structure. Okay. Inside the pipeline. Now you are seeing something here and here, which are not actually part of the pipeline as such, because they're all cache memory or actual instruction memory or data memory, which is outside the CPU. Okay, cache is also, it's not within the CPU, I would say, but it is shown as a part of the pipeline stage because something is to do with those memory is happening inside. So other than that, you are seeing some pipeline registers between stages. And as you can see, the width of this pipeline register, they are much more than what you see as a 32-bit registers inside the processor. So pipeline registers are a collection of bits, collection of values, which are required to be processed across the stages. So they are not restricted to only having few bits, but there is a limitation, but it is much more than the 32-bit value. Okay, it is capable of holding more values. And this pipeline register also carries data which is being exchanged between the stages, as well as some control signals. Suppose if add instruction is coming, ALU should perform add operation. Some subtract instruction is coming, ALU should perform a subtract operation. So that is a control signal for the ALU, which is also passed across the pipeline registers. But those control signals, which are not very obvious or very important, it is not shown here for a simplicity case, state, because if you show all the signals, it will be too complex to understand the main concept. So that is not shown, they are all ignored, but that doesn't mean they don't exist, they are there. So from the picture you will be able to make out which is instruction fetch stage, which is instruction decode stage, and executable stage, execute stage, and memory stage, and write back. Okay, that is the stage we are talking for quite some time. So during the simulation, I am going to talk about one instruction flowing through the pipeline. I am not going to concentrate on what happens when the, suppose our interest is this instruction. When it is in this stage, I am going to show what the instruction did here in the previous cycle, and then what happened even prior to that. So we are going to take a snapshot of what this instruction is doing on each stage. So you have to remember, in the real life scenario, when our interest, our instruction of interest is in this stage, this stage is occupied by some other instruction. Okay, in real life they will be occupied by some other instruction and some other action will be happening. Okay, Similarly here also. But in the picture, I am going to show the snapshot of what this instruction did to the pipeline. So it is not the real scenario. It is capture of what is happening here and here on every cycle what is happening. So we are freezing it once the instruction is passing from one stage to the other. So in real life, the instruction which is executing here will not have anything to do with these stages, and there will be some other instructions in these stages. Okay, some other action will be happening though in those stages. So remember that whatever is required to be passed on is given to the pipeline register so that the instruction can independently work with this hardware and with this input and generating this output. So it is like a individual actions happening. Okay, once it crosses the stage, that instruction does not have anything to any action happening here. The it will influence, it may influence, but some other instruction will be there. Okay, so remember that. Okay, now I want you to think, by now you might have studied the picture. You can see one more thing. In the original pipeline picture I showed, the register set was coming here as well as in the write back stage. But in this picture, we are showing it in one place. Remember, we are going into the pipeline and seeing how the registers and how the interfaces are. So you cannot have these physical registers in two places. So far, we assume register here and register here, right? Register set here. But we are showing in only one place because it is a physical location. But some actions are happening which is controlling the registers here. Okay, so though write back is accessing the register set, physically it is shown in one place, which is here. Okay, so these are the first initial idea when you look at the picture. It's not very complex. Once I show you the flow of the control, you will be able to understand. Okay, now I want to ask one question. Which is the first action happening when I say an instruction is getting executed in a pipeline? What is the first action in this whole picture? Where do you think that I should start showing you the action? You can reply me on chat. Yeah, I have disabled everyone. No, you cannot chat with everyone, but you can chat with me. So I am not seeing any answers. Can someone tell me what will be the first action when I am saying the pipeline is start executing this instruction? This instruction is going to enter the pipeline. When I say, what will be the first action? Anybody? Are you all sleeping? No response. At least one soul in the whole class. Am I audible, guys? Hello? Hello, hello, hello.
Hello. Yes, sir.
Yes, sir.
Why are you all in a sleepy mode?
No, sir.
No, sir.
Today is raining.
Raining.
Power saving mode.
Oh, you tell me, when will you be in totally awake mode? Okay, no response. As I told you, for the instruction fetch, what should happen? Instruction should be fetched. So PC should put the address out. Okay. So let me go forward. I am going to give you different color codes for different stages. Okay. And then first action is this. PC is giving out the address to access the instruction memory to get the code. That's the first action. Okay. Now I am showing some number. Don't think that value 1.0 is going through. No. I'm saying the numbering is shown as a, to direct our attention, it's a sequence number, okay? Sequence of events as far as this instruction is concerned. So don't get confused that I am showing some value or data which is flowing there. Actually, what is flowing is a address stored in the PC is given to the instruction memory to fetch the first instruction. In real life, it will be a cache, instruction cache. Now, if you see in the picture, the same address is also coming to the one adder. If you recall, I mentioned that the PC should be incremented by 4 because this is a RISC processor. PC should be incremented to next address for fetching the next instruction within this clock cycle, because once after this one cycle is over, this is passed across and this stage is busy accessing the next instruction. If it has to access the next instruction, it should have a new value on PC. So that means someone should add it with 4 and put the result back into the PC within the same clock cycle. Who is doing it? This adder is doing. We are not going to use this ALU for that purpose, which is down the line in the pipeline. It is meant for different purpose. So you can imagine now what will be the next action. I'm showing the same signal is coming. 4 is permanently given as an input. So this adder adds 4 to the current existing PC. Suppose if the current existing PC is 100, it will be incremented to 104 and it is loaded into PC. So it is coming out and loaded. Now remember there is a MUX there. Okay. So it may take input from either this or coming from this. Right now MUX is configured, there is a control signal, configuring it such that this output is taken in and it is fed back to PC. So PC will latch it. So it's a register like a FIFO, 32-bit FIFOs. So it will be latching the new address, which is 104 if our initial address was 100. So that happens. During that time, what is happening is instruction memory is being accessed. What will come out? An actual instruction, which is a instruction IR, instruction register content comes out. Where is it stored? As I showed you earlier, it is all stored in the pipeline register, IFID. Before that, I am explaining you control signal values to MUXes and passing between the pipeline registers are not shown here. Okay, I am not showing the control signal to MUX. Control signals are generated during the ID stage. Okay, based on the instruction, it is generated, and sometimes control flow instructions, which is branch, jump, those things will change the flow of some control signal. Do not worry about it. I have not spoken about control signals, control flow signals so far, instructions so far, sorry. Control flow instruction means jump, branch, jump on carry, those kind of instructions. I'm not talking about those. So ID stage is generating the control signals. Okay. Now what happens? New PC value is loaded and instruction is read. It is available here. So actually interface stage actions are done now. It has completed its job. It is ready for next instruction because it has incremented the PC by 4 and it has loaded the instruction which is read into pipeline register. So now the pipeline, one cycle is over. By within one cycle, this should be done. So now we can see what happens during the next cycle. I am showing the next cycle signals as cycle 2, cycle 2, which is a color blue or cyan. So as I told you, the instruction register is nothing but what is the actual instruction content is. It says opcode, what is the operand registers, whether it is R2 or R3 or 4, and then if it has a destination register, its number, which is whether it is 5 or 6 or 7. In our case, destination register is 1, operand one operand is 2, and this is 3. So these are all the actual registers to be accessed. It is showing that I want to access the operands R2 and R3 from the register set. So the register set should be given a signal saying that I want you to output R2 here and R3 here. right? There are two outputs and these are all control signal. I am showing the control signals as dotted line, and it is generated during this cycle based on the instruction which has been read. Because we read the instruction add R1, R2, R3, it will have R2, R3, R1 as the values in the instruction, which is taken and fed to the register set. So now register set is going to give the output. You understand these two. What about this? If you recall, I told the result is written into R1 and the writing of the result is happening in the write back stage, right? It's not happening before. So during this stage, it doesn't know which register it is supposed to write into. That information has to be passed across stage by stage. So I have spoken about it earlier also, which is shown here as R1. It comes only here. It doesn't come and write here. Please remember, there is some other instruction is working here. You hear some other instruction and there is something else. So you should not pass it beyond one stage. Okay. So it has to be passed stage by stage. Though the signal lines are shown like continuous line, don't think that the signal R1 will go through complete thing during this cycle. It will go here and stop. Okay, it is latched R1. Here, remember one thing, it is not passing the value of R1. If it has to pass the value in R1, it should have been taken from here. It is not passing the value stored in R1. We are not interested in knowing what is the value of R1 because we want to write into R1 at write back stage. So write back stage should know it is supposed to write into R1. So only the number saying it is 001, suppose, that is passed. If suppose destination register was R10, then number 10 will be passed because write back stage is supposed to write back into R10. So it is the information about to which register the result has to go is passed across and not the actual content of the register as far as this is concerned. Now what about this one? Operands. Operands, we want actual values because when the ALU is adding, it wants to add the values stored in R2 and R3. So it wants the data which is in R2 and R3, not the number saying R2 and R3. So the number saying R2 and R3 is coming to the register set and a read operation is performed and it is going to output the values stored in R2 and R3 onto this register. It is latched when during this cycle. So I am showing a thick line here, okay, not a dotted line. So data is flowing. What? How many bits? 32 bits. 32 bits of value stored in R2, which is inside the register set, is read out. And as I told you, it's a multi-port register. That means during the same cycle, two registers can be read and one register can be written into. So it has got two read ports and one write port. Okay. One more thing you remember, when this is happening, a reading of these operands is happening. If suppose I had an instruction in the write back stage, which was maybe add, let me say add, okay, it is add or 6, 7, 8. It was this instruction which was here and moved here and then it has come here. It is now in the write back stage. This instruction is in write back stage. It is all R, okay? That means what? The result which was computed by adding R7 and R8, which is available here, I will show you later on as we proceed. Now R6 has to be written into. When is it happening? During this time. When this R2 or R3 are going to be read out, parallelly a control signal from here, because the previous instruction would have passed down that value. So R6 will be accessed here and the result which was computed during the add operation will be written here. Now you will see that two actions are happening here. One is for reading the R2, R3 for this instruction, and at the same time writing the result of this instruction which was executed 3 cycles back. But if you remember, I said that the writing and reading are happening on 2 different cycles, half of the cycles. So writing happens during the first half, reading happens during the second half. So it is not at the same time. So same register set is used. R6 is loaded with a new value, and in the second half of the cycle, R2, R3 are read and loaded into this. So I'm just superimposing another instruction which likely to be or happens to be here. Okay. So if you don't understand, hold on, I will go further. But I feel with a lot of explanation so far I have done, you should be able to appreciate what is happening. Okay. So there is one write port, 2 read ports, which are happening, and writing is happening during the first half cycle and reading is happening during the second half of the cycle, and it is all done during this. Now R2, R3 values are stored. R1 is the information, control information, which is passed across. Okay. That's all. I don't think anything else has to be done here. As far as this instruction is concerned, operands are loaded, okay, into IDEX, which is this register, pipeline register. Now, next stage. See here, our instruction was add. So ALU is now informed, perform add operation. How it suddenly appeared here? It has come from here to here and then here, okay, which is not shown. That's what I am saying. All control signals are not shown here, okay. Otherwise, you will be wondering how suddenly ALU knows that it is supposed to perform add operation. How does the MUX know? These two MUX, how do they know? They have to choose this signal over this. They have to choose this over this. How does it know? It is because of control signal flowing from ID stage. Okay. So now look at this. R2 is coming here. MUX is choosing this value, what is coming from ALU, and this MUX is choosing the value which is coming from register set again. Sorry. Okay. It is taking the values from what is coming from here, which is stored here. So it is performing an add operation and then writing the result into pipeline register. So now what is written? The actual content of R2 plus R3, the added value. Okay. The sum of R2 and R3 is written into this register. Now I want to ask you one question. Is the job done or something else has to be done? Can I move to next stage, or I have to show you something else during this stage, which I have not yet spoken about? I want you guys to respond. This R1 should be passed across. Otherwise, you will have a problem, right? So during this cycle, result is written. Yes, I agree. And R1 is also passed, saying that for this instruction, the result should go into R1. So pass it across. Okay. So I hope it is clear. With no response, I am just getting worried. Please stop me if you don't understand anything here. Okay. Then now what should happen here? If you remember, it is an arithmetic operation. I told that data memory has nothing to do. So you can imagine what is the flow the signal will take. Okay. Which signal is latched. Those things you should be able to make out from the picture. It is like this. Don't think that signal is not going here. Okay. I am not showing. I am only showing what is of interest. It is also going here, but it will be ignored because MUX is not going to choose this signal. Okay. You are all electronics engineers. You should know how to read the circuit diagram. You should understand how some signals are allowed, some are not. So when this output is put on this bus, it's a bus. Remember, it's a 32-bit wide bus. It's not a single line. 32 lines are coming because the result is a 32-bit result. So it is getting written into this, okay, latched onto this one, And what else needs to be done? Now, I don't want you guys to miss out on something else. You should do one more thing, pass on R1. Okay. So this is the job done here. Data memory, nothing happens. It is not doing anything with the data memory. So no data memory access is initiated. It is not, these are not fed. These values are not read by the data memory. So it's all happening very intelligently based on the instruction. The flow happens. Okay. It's a very interesting to watch how it is really implemented inside a pipeline. That's why I took pains to simulate it and show it to you. Okay, this cycle is done. Next cycle, you guys should be able to understand what will be happening. It is choosing the value of this. It is not choosing something from here. Now, this R1 should go back. This control signal should go back to the register, and then the data, actual output of the result, which is to be written into R1, is now happening. The actual output of ALU has landed here and it is going back to register where it is supposed to be stored. And when you are writing, you have to say which register you are writing. So I should show R1 here, okay, implicit, because R1 only is coming here. It's a control signal. So write is happening. Now look at this. There is a blue signal here as well as the purple. Okay. So actually this blue is belongs to this signal instruction. In real life, there may be some other instruction getting executed or being in ID stage. So based on that, some read will be happening. During the same time, in the first half of the cycle, our instruction is writing the result, and then some other instruction is reading its operands during the same cycle, first half, second half. Okay. I hope this makes it clear to you. So far, whatever I have explained to you as a black box, I have shown it to you with a picture, with the actual circuit. Now you should have a very clear idea of how things happen. Okay. So any doubts so far? Let me see all of you. Cannot see all of you. Maybe some of you. Can you put thumbs up if you have followed so far? 43 says yes. Okay. So can I assume others? I am seeing Chacha Ketwe here. No guy thumbs up there. Okay. Now I am forcing you to say yes. Don't say yes if you are not followed. I'm okay to explain, but I want to know. I want to see at least partly what I am seeing is responding. Okay. So if you have understood this, if I believe you have understood this, I want you to do something here. I will do one thing. Okay. So it's a store instruction. That means it is storing some data from R5 into the data memory. So during the data memory cycle, it is supposed to write something into it. For writing into data memory, it should have an address and it should have a data. So let me say how you have to think solving this thing. If I give you an instruction, you can actually first understand the instruction, what it is supposed to do, then maybe go backwards. Okay, what I need, if I need to execute this instruction, what am I needing? What do I need? How do I get it? Then you go backward, you will get it actually. So you need an address here, you need a data here. Okay, you may wonder, how do I know this is an address and this is a data? Okay, that's a good question. You may think this is address and this is data, but you have to have some common sense and logic saying that address is coming from ALU because it is performing an addition of base address and the index, finding the effective address EA, which is coming from ALU, which is shown like this. So address must be coming here, and data should be coming here. Okay. So what is the cycle? Is it a read cycle or a write cycle? It is a store. You are storing it, writing into memory. So it's a write cycle. So you are actually solved the problem. What is supposed to be happening during the memory stage? You don't know what is happening here, but you know what is supposed to happen here. If you know this, then you can backtrack. Okay, what I need here, I need R2 plus 8 available here. That means what? I should get R2 R2 from the register set. Where else can I get? And if it has to be got, it should be available here, R2. Okay, R2 I am getting. Now where do I get ampersand 8? Immediate constant. Do not assume immediate constant is coming here because it is not inside a register. Immediate constant is part of the instruction which is available here. And if you see that there is a path, and I mentioned that sign extension is happening. The immediate constant is stored as 16-bit value in the instruction, and it is extended, sign extended. So because I am showing a positive value here, I may show something like 16-bit value, which is FFF04, which is a 16-bit value, and sign bit is 1. This is a negative offset. So if I need to perform a 32-bit addition, I should make the 16-bit value into a 32-bit value, which is sign extended. If a sign bit is 1, I should extend the sign bit as 1. So I should put F, 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 F. Okay. So this is the 32-bit value offset, which is getting computed from the instruction and fed to the ALU. So how will it come here? So now see the path. You know that constant is coming and then it is landing here. Now you see a line coming from here to this. Very good. Then this mux should choose this in signal and not an output coming from here. Okay, very good. Then you know inputs have come. That means if it is taking the constant, which is ampersand 8, in this input, what should come here? It should be R2. That means if it has to be R2 here, okay, you have backtracked it and said, I want R2 here. That means it has to be from here because it is showing this signal, which is a PC. It is something to do with the PC value. So it is not the one. R2 has to come from the register only. That means R2 should be available here. Okay. And then mux should choose this signal and not this signal. So you are now clever enough to find out R2 is coming here. That means you are partially you have solved the problem of computing the address. Very good. You know how the address flow. This is not there. Okay. Please don't confuse with this signal. Okay. So I will show you a proper signal later on. I am just rebuilding and I'm just trying to make you think. Now I need R5. R5 is that data which is to be written into memory. That means if it is an address here, there should be a data here, should be available here. What should be available? In our case, R5 should be available. That means it has to come from here only. That means register set should output R5 on this and R2 on this. Okay. And the constant here. And it should choose this signal. It should choose this signal. Address is computed. Data is available. Perform a write. Your job is done. So you have seen the complete flow now. This is how we should think when I give you an instruction and then make you draw the picture. So now let us quickly go through it, whatever I explained. Okay. Any doubts, please stop me. So same thing happening. It is computing the new address. Nothing different. It has to keep doing that. And then based on the instruction which has been read, right now we are thinking that the instruction is store. So it will do this R2 control signal, R5 control signal, and the actual constant 8 is coming. Sign extended value, 32-bit value is stored here, and R2, R5 is coming here. Now R5 is not needed for ALU. It is needed for the next stage, but it has to be read during the operand read. See, this is also an operand. Don't assume that only what is given to ALU is an operand. Operand is the input needed for an instruction to execute. Operands are the inputs needed for an instruction to execute. So R5 is an input to the instructions for store operation to be successful. So R5 has to be read, and if it doesn't read it during this cycle, R5 cannot be read at all. So it should be read during the ID stage. Okay, but it is not used immediately. It is passed across. If you see that R5 is passed as a solid line, I am showing it because this picture doesn't show like that. Okay, similarly this is a solid line and he is showing it as a 16-bit and 32-bit, so you can understand that which is data and which is control signal. So now what is happening, this constant 32-bit constant is flowing through this. ALU is computing the effective address. It is available during the EX stage. It has computed it. Now one more job has to be done. This should be latched. Okay, so there will be a control signal to latch this value. Okay, so what is the value latch? R5. Now we have a address and data ready for the next stage to perform its job, which is the writing into memory, which is happening during this cycle. So as far as this instruction is concerned, job is done. Nothing else is there to be done during the write back stage. So there is nothing flowing here. Okay, remember there is something, the signal is all connected directly, so but it is not latched or used. Okay, so the control signal operates such that based on the instruction, some paths are enabled, some paths are disabled, some paths are ignored, some data may be available, they are ignored. So it all depends on how the implementation is done. But if you are all hardware centric and you want to know how things go, how they happen, this is how it happens. Okay, so now data is written and this instruction has nothing to do here, right backstage. So our job is done, but one cycle will be lost. Please remember that. Okay, I hope this is very clear. Now you are all now ready for load. Don't think that I am going to spend time here explaining this. Homework. Do you know you are at home? Don't say that I am attending class from home, so I am doing the homework now itself. There is no homework needed. Offline work, please do it. Take the picture and try to draw. Either you can draw roughly or think about it, and then I don't know whether I will share the answer because I don't plan to. I want you to do it. Okay, it is easy, but be careful. It is a load operation. That means it is loading from the address this. So it is not same as store operation. That's all I can say. It is a combination of first two I showed you. Okay, if you understand, it's a combination of what happened during the first two instructions, add instruction and store instruction. It's some part of it is to be done here. I am sure many of you should be able to do. I expect you to do. It is required for the test 1. Okay, the knowledge that you gain is required for the test 1, not the actual question. I'm not going to ask the same question in the exam. Okay, okay guys, so let us now go to pipeline hazard. Okay, what is a hazard? Let me explain first what is hazard. Hazard is a danger or a risk, something which should not happen, but it happens. If it happens, how do we handle it? Okay, so we are going to talk about what are the hazards it can happen because of the pipelining, and what type of hazards, and how do we address them through a hardware solution or a software solution. Okay, there are possible ways of many ways of solving it, using either in hardware or in software, or in combination. Both hardware and software work together to solve some pipeline hazards. Now let me give you some little bit of overview. Why are we talking about suddenly hazards? Normally, instructions were executed one after the other. Okay, so far we have seen in computer organization, and as well as in the first class, I showed you a CPU structure which is performing all the job belonging to an instruction in one go. It will do all the job. I'm not saying it will do it in single cycle. Please remember, I'm not saying it will do it in single cycle, but it will do all the jobs related to one instruction completely and then take up the next instruction. If I have to give you an analogy, suppose you are having 5 exams in your comprehensive exam in a normal semester flow. You are asked now to write one exam at a time. 3 hours are given, write one exam. Next day come 3 hours, you write one exam. It is much easier for you to write one instruction, one exam at a time. But if I tell you suddenly, MIT has changed the logic, it is going to conduct multiple subjects together. That means you will be asked for attending the exam for 3 hours, but first 1 hour one subject, second 1 hour another subject, third 1 hour some other subject. You have to do it, and then afternoon, remaining part A of one exam and part B of next exam you have to write. Imagine a situation if you have to do that, how horrible it is, how difficult it is. You have to do a context switch within the day, within the exam time. You are doing it now between days, but doing it within the exam time is much more complex. Similarly, we are expecting the CPU to perform instruction execution every cycle. Change the instruction you are doing. You are telling the part of the hardware to execute part of the instruction, and then in the next cycle do something else, whereas some other part of the hardware is doing something else, processing it. So you are splitting the execution of an instruction into multiple stages. So it has got its own problems. Okay, so let me explain what are those problems now. There are situations called hazards that prevent the next instruction in the instruction stream from executing during its designated clock cycle. So I have set of instruction. When we are writing the code, assembly code, we assume that this instruction is completely executed before this is taken. See, our mental makeup is the CPU is unpipelined. We assume these instructions are executed one after the other, unpipelined, and we think this instruction is completed and it is generating some output on some register R1. When the next instruction is starting, R1 is already having the new value. That is our mind, our thinking, and we write the code assuming like this. Not only we as a human being write, even the compilers generate the code assuming this sequence. Now, as I told you, the pipeline implementation is transparent to the user. When I say transparent to the user should not be bothered to the maximum extent that, hey, think about the pipeline and arrange your instructions such that there is no dependency, because it is not humanly possible to do that. Okay, you cannot expect the programmer to know internal details of this, whatever I showed you now, that 5 cycles it takes for that some result to be returned. So I have to arrange the instruction such a way that no hazards are happening. You cannot expect the user to do it. So how do we solve it? We should solve it in the hardware. We should identify the problem and try to solve it. That is what we are trying to do now. Okay, so let me see the time. I will take another 10 minutes, 1 hour, we'll break. So there are situations for hazard that prevent the next instruction in the instruction stream from executing during its designated clock cycle. It is supposed to be doing something. We have split the pipeline. So we are preventing some other instruction in the pipeline to do its job because it has a dependency with the previous one. I have explained something earlier. We'll again see that now. This phenomena is it will disturb the smooth execution of the pipeline. Okay, pipeline cannot move forward smoothly. Hazards reduce the performance. Now, if suppose there is a hazard, you cannot prevent it. You have to, if you want to prevent it, you have to stop executing. You have to stall it. You have to wait for the result to happen. So when you stall, what happens? The pipeline is not full. If the pipeline is not fully occupied with instructions, you are not going to get one instruction coming out every cycle. If you remember, speed up is assuming we get one instruction completed every cycle in an ideal steady state, which is not going to happen if there is a hole, if there is a bubble in the pipeline. If the instructions are stalled, our pipeline is not doing the job. We are making it to do nothing. In that case, we are going to affect the performance. The expected speed up is not going to happen, which is wrong, because we went into implementing the pipeline, put all the hardware design and design so much that, like what I showed you. After all this, if we are not able to make the pipeline always full, we are doing a injustice. We are not getting the benefit out of the hardware the hard work that we have put in. So we have to do something. So, but stall will happen, but we will try to address it. Okay. So pipeline may have to stall one of the instructions which is coming next. Now, stall means stop or cause to stop making a progress. Okay. Remember, stop making a progress. We are not stopping it permanently. We are not telling that one instruction cannot be executed at all. That is, if it happens that that instruction is illegal instruction. If it is an illegal instruction which is read from the memory, instruction decode cannot understand it. You cannot make it work. You can say it is impossible to execute it, but it is not an illegal instruction. It is a valid instruction, but it cannot be executed now. After a few cycles, it may be executed. So you have to allow it to wait. Remember, and if you recall in the OS course, I showed about page fault. Page fault happening. What is it? CPU is trying to access a memory which is not in the main memory. Virtual memory, if you thought of, it was in the hard disk. So page fault also is similar to this, where that actual data or instruction is not in the main memory. So it stops the execution of that access, memory access. And then it goes to the virtual memory paging and brings the new page from hard disk to the main memory. And then the memory read or write happens. So during the page fault also, the instruction is stopped. Only thing is that is longer time. The stopping is not going to be for few cycles. It is going to be for many cycles, because getting it from the hard disk to the main memory is hundreds of thousands of cycles. So what will happen is that process will be taken out, not that particular pipeline. We are not stalling the pipeline. We are taking the whole process into out of it, CPU, and bringing a new process into CPU, and the pipeline is running. The whole process is now out. So if you relate what I told you during the page fault, what happens, and the pipeline, you should be able to understand what will really happen now. Memory access is trying to create, make a page fault. Now what will happen is that instruction will be re-executed. I mentioned it in the OS course. The instruction which created a fault will be started again. That means what? That instruction may either load or store, or even PC access will be started again. Pipeline will be filled again. So it will come through the pipeline again to execute that instruction. So page fault is much bigger image, bigger impact, and a simple instruction level hazard is a very minute level problem. Okay. So it is like a small hazard. page fault is a big accident. Okay, you cannot just make everything stop and then do. We have to do a major job. OS has to be involved, virtual memory should be involved, disk access has to be involved. It's a big job. Okay, I want you to think all this when you are studying this. It will come only when you are really interested in learning and knowing what is happening. Okay, it is, if you are studying this course, attending this course for passing this and getting some grades, it will not happen. You should think just to learn, nothing to for scoring marks. Okay, then you will become a true engineers. Okay guys, a stall is a pipeline bubble, one hole. Okay, it's a small disturbance to the flow of instruction. It's a small disturbance. I'm not saying like a page fault, which is a bigger impact. It's like an earthquake. Okay, from the table, one glass bottle falling is a small hazard, whereas whole building shaking is a bigger hazard. So fault is like a bigger effort. Okay, now I will quickly explain to you this. I have already told you an instruction is flowing, two instructions. Okay, like one after the other. The result is into R3 here, and an operand is from R3 here. These two instructions are coming one after the other. If you remember, I showed this same instruction happening with a gap, with few no-ops in between. But if they happen to be one after the other, there will be an issue. How? By now you should be able to understand where is the issue. This R3 is written into during this cycle when this instruction flows through the pipeline, whereas this instruction wants the operand to be read during this cycle itself, because reading is happening during the ID stage. Now suppose if I allow this instruction to go further, what will happen? I will have a wrong value of R3, whereas as a programmer I have written it like this, assuming that the result of this addition is available for me for the next instruction. If I do not execute in the same way the programmer wanted it to be executed, my CPU is not doing its job. It is doing what it wants to do. It is accessing some R3 value which was prior to this, whatever value was there, it is accessing it and adding it. Your program will never work. Whole thing will fail. It is not possible. If you sell a CPU like this, your company will be bankrupt immediately, the next day. So we should build a CPU which is reliable, which will execute the instruction the way it is supposed to be. So I have explained these things. Okay, very obvious. I don't want to spend time. So I cannot proceed further. So I have to stall this. This stage has to be stalled. That means until this is done, I can't execute this instruction. Now, what is the impact of this? If I don't move this instruction further down the pipeline, I can read one more instruction in the next cycle. You know, in the same cycle, I can read one more instruction, but not beyond that. Anything beyond cannot happen. So if an instruction gets stuck in a pipeline, even the instruction coming behind will also be stuck. So you cannot keep accessing instruction if the pipeline is stalled. You have to stop accessing the instruction memory, because there is no place to hold it, because instruction fetch cannot take the new instruction until this is moved. This cannot move until this is moved out. If it is blocked here, nothing can happen beyond. Okay, I hope this is clear to you. So R3 is only getting written here, and it wants it here. It wants it in CC3, whereas CC5 only it is available. So it has to be a stall. Okay, what is it called? It is a read after write hazard. Let me explain how to understand this. Okay, raw hazard. Read after write. That means I want to read R3 after this instruction write into R3. Okay, that is my intended behavior. Read this after this instruction has written. So it's a RAW. I am not able to do this RAW because of this hazard. So it's a raw hazard. Raw is my intended behavior, and the hazard is preventing me from doing it. I want to read R3 after the R3 has been written into. Read after write. So this is how you have to understand. Okay, let me quickly update it. Pipeline hazards are caused by dependencies. Dependencies are property of programs. Okay, normally data is flowing through the pipe, no instructions. Two instructions are data dependent on each other. If they are dependent, they cannot execute simultaneously. Dependence results in a hazard. Okay, if there is a dependency, there is a hazard. If R3 was not used in both the instructions, there is no problem. There is a common data. When instruction is stalled, all instructions issued later are also stalled. As a result, no new instructions are fetched during the stall. Okay, no new instructions are fetched. I explained to you already. So instruction issued earlier. Okay, one more thing I will tell you before I stop. Suppose stall has come here, but nothing prevents this instruction passing from each stage to complete. Don't think that if one stage is stalled, only this behind it will be stalled, not the front one. Okay, they can go, they can proceed. Let me give an example. In a airline check-in, suppose one passenger has some issue with the data boarding pass, that person will be stopped. Not that those who have cleared the boarding pass and getting into the aircraft will be stopped, but the person behind the queue will be stopped. This guy will be talking to the airline staff and then delaying the whole thing. That's what is happening here. So the previous instruction will be continuing. One more thing here, important thing is, when the previous instructions are completed only, the condition causing the stall can be resolved. Condition which is causing the stall can be resolved. Why? If suppose you are waiting for the previous instruction to write into R3, until that instruction is executed, it will not be written. If it is not written, the next instruction cannot read the R3 value. So it has to complete it. You want the previous instructions to be completed for the condition causing the stall to be removed. Condition causing the stall to be removed, the instruction causing the stall should be executed. Okay. There are three categories: data hazards and structural hazard. Okay, I will talk about it. Okay, don't worry about it. It's all happening because of the relative timing of the instruction. Because of the overlap of execution, it is happening. There are three types of hazards: structural hazard, data hazards, and control hazards. Okay, so with this, I hope I'm stopping here. Let me resume. Okay, before I continue further, let me again tell you, we were talking about hazards. Okay, that is, let me summarize again what we mean by hazard and what we want to study about hazard. So normally instructions are executed one after the other in an unpipelined CPU, and programs are written assuming that instructions are executed one after the other. We do not assume that instructions are split into sub stages and they are all executing in parallel through a pipeline. We never imagine while writing the code. So we expect the CPU to handle it in case it is trying to execute the instructions into multiple stages. We don't want to take the burden of how it is done. So that is the job of the CPU designer to handle it. Now, because of this, the instruction normally assume one instruction is completed, the next one is taken up, and so on. So I can write a code where the result of the first instruction is immediately required for the next instruction. I can write the code, it is not wrong. It is the CPU which is doing something internally, which is not my botheration. I will write my code the way I want, because CPU has given me, the designer of the CPU, set of instructions, and they said you can use any registers, you can perform any arithmetic operations, and you can call one instruction after the other. Now, when I do it, because of the pipeline, if there is an issue, that should be handled. Now, there are certain things can be handled in the hardware, some things cannot be handled. In that sense, it has to be delayed. So such instructions have to be delayed. So one thing I want you to understand, having a dependency in the instruction, not illegal. It is not an illegal thing that you have put two assembly code which depends on each other. Whereas if an instruction memory is corrupted and there is a wrong instruction opcode which is coming into the CPU, I don't expect the CPU to perform anything. But at least it should identify that it has read the wrong instruction and stop the CPU. Raise an exception, illegal instruction exception, so that user will know that either memory is bad or my program compilation executable code is wrong, something has gone wrong, that CPU is not able to handle it. So such things are allowed. CPU cannot say, I will execute whatever junk you give me. But if it is a valid instruction, but there is a dependency, it has to be handled. So there are different types of hazards, okay, which can be caused because of the way instructions are arranged. One is structural hazard. Structural hazard means it is something to do with the hardware module in the CPU. Some module is not available. It is busy with something else because of some other execution instruction. So it's a structural hazard, something to do with the hardware module. Data hazard. It is some data dependency between instructions. Because I want a result of the previous instruction, which is not yet completed, it's a data hazard. So there is a data dependency because of which I am not able to go further in the execution of instruction. So it's a data hazard. Control hazard is something to do with control flow of the program. We have not talked about the control flow so far because it is more complex. I have deferred it for some time because I want you to be very strong in handling those data related stuff before coming into control part. But you guys know instructions like branch and then jump on carry and then BNE, branch not equal to, branch equal to. There are so many instructions you have seen which are control instruction. That means the flow of instruction changes. The program counter has to be modified when the control instructions are seen in the code. So far we have seen data instructions, all arithmetic instructions and load store instruction we have seen, but we have not seen any of those control instructions which impact the value or which change the value of the program counter. So far all the instructions are in the sequence, PC keeps on incrementing. That's what we have seen. So any hazard due to those instructions will be seen there. Okay, I will come to that. It's going to be more complex than what you have seen so far. Okay, very quick example. Suppose I have an L1 cache which is unified. That means I do not have a separate data and instruction caches. I have them together, but I have a cache, but it's a single L1 cache. Why I mention L1 is it's a cache which is closer to the CPU. Okay. And let me recap whatever you guys are supposed to know. CPU is there. You have a L1 cache, unified cache, I'm saying. So both code and data can be there. There is a single interface, address and data. So either CPU may be reading an instruction from here or it may be reading a data from here. Now, how many cycles? It will take only one cycle. Assume my CPU interface with the L1 cache is such that if there is a hit means that code or data that you are looking for is in the cache already, then it's a cache hit. So it can be read in single cycle. So I can finish the instruction fetch in single cycle. I can also finish load or store in a single cycle. But it cannot happen together. Why? I have only one interface, one address bus and one data bus connecting to the unified L1 cache, which is holding the instruction or code and data in the same cache. Even if I assume whatever code I am looking for and whatever data I am looking for is available in the cache, that means it's a hit, it's not a miss. If there is a cache miss, it has to go to further down, either some other cache or the data main memory. So it will be few cycles by the time you get it. So I am not talking about that condition at all. We always assume, our discussion is assuming it's all available in the cache. So it's that means what? It has been fetched previously, a block of code or a block of data, and which is available in the cache. So I don't need to go to the main memory again when I'm explaining this concept, because it is simplifies my explanation. And it's a having a cache miss is like a bigger accident. Okay, we are talking about smaller hazards. So let me come back. Now I have only one interface connecting CPU to the memory, which is cache memory, and it's an L1 cache, and which is a unified cache. So there is a possibility when the instructions are executed, if there is a load instruction, that means what? I want to access the data memory for a read purpose. I want to load a register from the memory. I'm not storing something, so it's not a write access. I am doing a memory read access. Now there is a problem. I have only one interface. If I have to access the data, I have to put the address of where the data is, which address, and if it is available in the cache, it will be given. But I can't put both code and data together. I can put only one of them. But all of you know, during the pipeline stage, when one instruction is in memory stage, down the line, okay, 3 instructions behind, this instruction I plus 3 will be in the fetch stage. That means it is trying to fetch the instruction, a new instruction from the instruction memory, which also happens to be in the cache. I have only one bus. I can't do 2 reads simultaneously. And I can't do the way I did it for register. Okay, I can't say I will do it during the first half cycle, no data memory access, second half cycle I will do a instruction access. It's not possible. If you know how memory works, how address is put into the memory, and how even if the cache, even if it is a cache, data has to come. So there is a time investment there. You cannot do it in a half cycle. Okay, register read is different. You can do it on one single clock edge, whereas memory read is you have to put the address. It should be stable enough on the bus, and you are putting it on a 32 wide bus, and it takes its own time. The distance between the CPU and the cache is also large, so signaling settling time also is there. So it's not possible like reading a register in a half cycle. Can I do it in memory? Is you need to have a much bigger, much high speed memory. We are not talking about that kind of a interface here. We are saying that it is not possible having two memory accesses, different memory accesses during the same cycle on a single bus. So how do you handle it? You have an option. Okay, let me explain to you. I will ask you a question. How do you solve it in a hardware? When such accesses happen, and it is likely to happen every time there is a memory access, there will be some instruction access happening. Which one will you stop? Will you stop this or this? You have to allow only one of them. Okay, because there is only one bus, I need to allow one of them. Which one will I stop? maybe I should have put a quiz for it, which I thought I didn't think about it before. If you guys say, I will stop the memory read, I will give importance to instruction access, you are wrong. I've told you that only one can happen. In that case, you have an option in the hardware to allow one of the accesses to happen. But if you decide in the hardware, I will stall this, but I will allow this to read, does it make sense? Because let me see the impact. By now you should have got it, why it doesn't make sense. If I stop it, what am I doing? I am creating a bubble here. This instruction cannot proceed further. I have stopped. I have stalled this instruction. This load instruction is stalled. Now, having stalled the pipeline, what is the use of reading the next instruction and then keeping it in the pipeline? Anyway, instruction execution is going to be stalled. This instruction cannot proceed further because the previous instruction there is still stalled. As I told you, when there is a pipeline hazard, you should give a priority to the instruction which will clear the block, which will make the pipeline proceed further. Now, if I do something, instead of this, if I allow this to go and then I stop the instruction access, now what is the advantage? Memory read will happen and this instruction will go to the write back stage. During that time, if suppose there is an arithmetic instruction is behind, it will also come into this. It can proceed. This also can proceed. Only this fellow has to wait. And once this memory access happens, this instruction access will be allowed and it will proceed. Assuming all these instructions also do not have a memory access involved. If all of them are having memory access involved, if your priority is to give always the memory access first, every time you will get a hazard, structural hazard, and all the memory accesses will be cleared. Now there is no instruction in the pipeline to be executed, and finally this fellow will get a chance to execute or fetch the instruction. So I want you to think little deeper. What if I have another memory read instruction? Lots of load instructions have come. What will happen? All these are all load instruction or store instruction. What happens to the pipeline? If you think, there is a lot of things to think about. Okay, I want more questions like this to come from you. I never get anything at all from any of you. That means you are not even going home and thinking about this. I am telling you what I am teaching is only the tip of iceberg. Below there is so much is there. If you do not think ahead and learn, you are in a final semester. Nobody is going to teach you. This is the maybe a contact class, last contact class that you have on a technical subject. You will go into a project, then out into the industry. Nobody is going to come and teach you anything. If you cannot read on your own, if you can't understand by reading books, you are not going to make progress. You will be stalled in your career pipeline. If you want to keep executing and then keep going in your career pipeline, you have to be continuously executing. That means learning on your own. I am not seeing that happening now. Even with the students who are interested in learning, I am not getting any questions. I am not seeing any interaction. I don't see any interest. The amount of work I put in, none of you are putting.
I sent you many questions, but you are not seeing
When did you send?
on chat.
You can send me later, right? I never tell that you have to send me in chat, and then in fact I answer all the questions. Okay.
No. You are not seeing my questions for today.
Oh,
there is error.
I'm sorry. Yeah, okay, that is okay. My discussion about what is happening is outside the class. Okay. That doesn't anyway. Let me 1 second. Let me stop sharing. Okay, so please stop me if I am not seeing your chat. It is not popping up always. Okay. Okay, guys. So this I have explained in detail. So let me go quickly. when different stages of instruction in the pipeline need to access both instruction memory and the data memory during the same clock cycle, there will be a structural hazard. See one thing, it will be a structural hazard only if there is a common unified L1 cache. Okay, we are assuming, okay, one second, sorry, let me complete this sentence. How do we solve it? Okay, one way is to solve it, another way is to provide a two different instruction and data memory and provide an interface so that they all happen in parallel. Okay, that's a solution, permanent solution, because we are going to see this kind of a structural hazard very often. As long as you have a load and store instruction coming, you will have this hazard always. So you cannot stall the pipeline for everything, then it is not effective. So a pipelined processor will get a better performance only if at least it has two different caches for data and instruction. Then only this hazard will not happen. Otherwise, having a pipeline is a waste. You have a CPU with a 10 stage or 20 stage pipeline, but instruction memory and data memory are unified cache, then you are not getting the benefit of all the design work you have done in the CPU. So it's a waste of effort. Okay, so we assume always in our processors dedicated cache is there. That's why we have seen instructions load and store happening parallelly. In the background, we always assume it is having different instruction memory and a cache memory, and it's a Harvard architecture which is accessing both simultaneously. Okay, I hope you are able to understand this. So let us quickly now come up, see what are the other things you should know. Two or more instructions requiring access to the same resource at the same time. Okay, one instruction having a requirement of an access to resource is okay. If two or more instructions needed, it will have a problem during the same cycle. Okay, at the same time means during the same CPU cycle. Resources include memory, caches, some bus, registers, ports, IO ports, and any functional unit. When I say functional unit, it could be a ALU, okay, or a multiplier. You will see more of these things. Okay, so if you have such requirement hardware, there is a limited hardware resource and multiple instructions need access to them simultaneously at the same clock cycle, one of them need to be stalled. Okay, that is a solution. You can solve it in the design stage, but once the CPU is built and the instructions are there in the pipeline, you cannot say that I will bring another ALU suddenly. It cannot be, it's not possible. So it will be stalled. There is one, you should be able to at least identify there is a hazard. Okay, that is very important. You cannot build the hardware such that it doesn't even know that there was a hazard. That's a tragedy. So you have to identify it and stop one of the instructions so that things will proceed. Okay, that is the solution from the hardware perspective. So, and unified examples are unified cache, and then there are when different stages of instruction pipeline need to access instruction and memory. Okay, this is the same thing I have explained. Now, what are the solutions? What are the possible solutions? Duplicate resources. You separate the memory into duplicate buses. You have a separate buses, two different ALUs. Instead of one single integer ALU, have two ALUs, or dual port memories, multi-port memories. All these are all solutions for having solving the hazards, structural hazard. Now, how do you handle it? Suppose hazard has happened. Okay, you have not built a duplicate resources. Hazard is going to happen. You should identify it and then resolve it. So identifying is hardware that performs resource conflict arbitration. So there is some hardware which will be doing a arbitration. Suppose, let me explain what I mean by arbitration. There is a module which is called arbiter. there is multiple, suppose CPU, it's a multi-core CPU, multiple CPUs, okay, need access to a common bus. This is a bus, common bus, and this is a arbiter. Arbiter is a hardware, okay. So when multiple CPUs try to access the bus can be given to only one of them. So arbiter identifies that this CPU also wants it, this CPU also wants it, and it will resolve the conflict based on fixed logic. Suppose this is CPU 1, this is CPU 2. The CPU ID with the lower number will be given a higher priority. Okay, some logic will be built into the hardware so that always when there is a conflict, the lower number will be given. That means this will be stopped. This will go further and access the bus, and it will relinquish the bus. Then the next fellow will be allowed. So it will be waiting. So if you remember, CPU memory interface always has a wait signal coming from the outside world. So when the wait signal happens, the CPU stops. It stops the cycle. It doesn't go further at all. It is like a frozen CPU. So until the bus is released, CPU stops, and then it will start again. Okay, this is how different hardware implementations are. You have to read on your own. Quite a lot of things are there to read on your own to learn. So hardware that performs resource conflict arbitration and interlocks one of the competing instructions. So in our case, it's an instruction. Interlock means a device or mechanism for connecting or coordinating the function of different components. So suppose when two instructions are trying to access one resource, it wants one memory. One instruction will be stop, another one competing instruction. One instruction will be stopped, another one will be allowed. Okay, so that is how it is resolved. Okay, this makes sure that one instruction proceeds and another one stops. So interlock is a hardware that starts the pipeline, inserts a bubble when a hazard is detected until the hazard is cleared. Until the hazard condition is cleared, the instruction is stopped. Once the instruction is stopped, the pipeline is stalled. The other instructions behind will also be stopped. But the instruction before this condition which caused this hazard will proceed. Don't think that whole pipeline will come to a standstill. It is not. Only the portion which is causing the hazard will be stopped, and the behind one, the one which are coming behind the stage. The stages which are ahead of it will proceed further. CPU clock will be running and they will be going forward. You have to imagine those things clearly. Okay. Now, let me talk about, this is all about structural hazard. Let me talk about data hazards. We have already spoken about it. Let me give you an example and then categorize it. Okay. Data hazards occur when the pipeline changes the order of read and write accesses to operand. When you are accessing the operand, in the pipeline, if you see, operand is read in this stage, and then later on the result is put. So some reading happens, and then writing is happening here. So we are not actually doing it together. We are splitting it into multiple stages and doing it. So it arises unavailability of operand. For example, if an instruction I, which is in the come first, occurs in a program order before an instruction I plus 1, okay, and both I and I plus 1 need a register which is X, some R1, R3, R5, some instruction X, sorry, some register X. Now, there are three different types of data hazard. Okay, let me explain. Instruction I is there, I plus 1 is there. It's not only this I plus 1, even I plus 2, I plus 3 can be there. For a simplicity, I am talking about this, or maybe I will say J. Okay, maybe I should remove this I plus 1 and make it J, because generic, it can be in any order, any instruction I or J. Okay, imagine I or J. I will change it. Instruction I wants to access some operand, some R, which I am calling it as some X, and J also wants to access X. Now, I is coming first, J is coming next. Between these two instructions, whether there are so many combinations. See, instruction I may need X for either read purpose or a write purpose. Similarly, instruction J may want to access the register X for a read purpose or a write purpose. Now, can you tell me a combination which does not cause an hazard? Which does not cause an hazard? Let me take another color. Imagine this I wants to access X for a read purpose and J also wants to read X for a read purpose. Both are reading from X. Is there a problem? Whatever order you do, provided there is nothing, no changes happening to X, okay, the variable register X, you can read it in any order you want. I before or J after or J before I, doesn't matter because it's all reading. So you will not get a hazard which is caused because of two instructions wanting to read a register from the same register. They are performing a read operation only. There is no harm. The problem will happen in all other combination. If one guy is write, other one is read, or one guy wants to write, other also wants to write, there is a problem. You may wonder why two writes are having problem. I will explain. So this instruction I also wants to write into a register, J also wants write into a register, but if that writing does not happen in the order in which it is supposed to happen, that means I came first, J comes next. That means write of I should come first, happen first, and then the write of J should happen. If the order is not maintained, you will have a problem. Okay, let me explain now itself. Suppose I, J, and then there is another instruction K which is coming next. As far as the program flow is concerned, instructions are supposed to be running like this. Writing of some value by I happens first, this next, and then this. In this K instruction, assume it wants to read from the same register X. K instruction which wants to read operation, it wants to do it on the register X. It is assuming the write happened just prior to this. This result is available here, right? It will assume that this write has happened just now. So I will be having the result of this write and I can read now. But if for some reason this writing is not happening in the order we wanted, and this is happening first and then second, this is happening first, this write is happening first, okay, then this write is happening second time, and then after a few cycle, and then this instruction is trying to read from the same register X. Now its value is not what was written by the J, it is by this I, which is wrong, because as per the program flow, I wanted this value to be available here, whereas it is happening because the order is changed. I am getting this value now, this value is lost. So even writing into a register, if it is not happening in the order you wanted it, it will have an issue. So reading, writing combination, if it is not happening in the proper order, there will be an issue. Writing of registers, if it is not happening in the right order, there will be an issue. Only two reads can happen in the wrong order, provided there is no write in between, there is no issue. Okay, so by now you will know that which are the possible causes of data hazards. It's only between read and write into a common register, and it's not read and read. So you are getting read after write, write after read, write after write. So these three combinations of data hazards we get when we have a common register, okay, being accessed by two different instructions. Let me call this as a I, the later instruction as J. Then there will be a hazard when this order is not maintained. That means we expect, as per the program sequence, instruction I should be executed first, then J. If it is not happening because of the pipeline, J is allowed to do some operation and then I is allowed to do something on the same register because of the pipeline. Then there is a hazard. Now, how do we solve them if any one of these conditions happen? So what we need is to solve this problem. First of all, we should identify there is a problem in the hardware when the instruction is coming in, and then try to enable some control signal so that either we solve it using our solution that we built in the hardware, or stall the instruction so that the impact is not there. Impact is performance wise impact is there, but correctness is assured. You are stopping the instruction, so performance is affected, but you have detected the hazard and you are not allowing the instruction to execute taking a wrong data. So you have made sure correctness is assured. Performance is impacted, correctness is assured. So that is okay. When you have two choices, either whether you have to have a correctness in the execution or speed, which is important. Correctness is important. That's why I slow down my class, even though I am expected to complete so much, because I want to make sure you do understand what I am saying. So correctness is more important, your understanding is more important than doing it fast. So we will stop the instruction rather than going ahead by taking a wrong values. Okay. So how much time we have? Maybe 4 minutes I will take and then we'll stop. Okay. So now I will explain with the instruction now example so that you understand it what I am saying. So I am going to change this I plus 1 to j to make it generic. Okay. Some I and some j instruction. Okay. Assume we have to have a generic statements. So let me show everything and then show you the example and then explain. Read after write. That means what? I am supposed to read a common register X. In my case, in this example, common register is R3. Okay. I want a read after write. You can easily make out from this which instruction wants this read after write. This guy. I want to read R3 after I has written into R3. That is what my intent is. When I wrote the code one after the other, I expect R3 to have the value of R1 plus R2 to be used for my next computation R3 plus R4. Maybe I'm doing a cumulative addition of values. So I need to have this value. I cannot proceed with this instruction until this has written the result into R3, or I have the value of this R1 plus R2 with me. Please remember, either the return should have happened, or even if you are not written, if you can tell me what is the value you got R1 plus R2 here, I can proceed. I don't care whether I am getting it from R3 directly or through some other means. I am just telling you this so that you can start thinking what I mean by this. Okay. This I am actually revealing a solution for this problem. I want you guys to think. Either I want the value from R3. In that case, I need to wait till this instruction completes writing into R3, or I am happy if you give me whatever was computed, give it to me directly. I proceed with my values. I execute it. I don't have an issue. Correctness is assured. So I'm actually revealing the solution for this hazard now. I want you to think from the instruction pipeline, how will you implement it rather than waiting for writing directly into R3, getting the result in between. Before it goes to R3, you are giving it. If you see some restaurants, when you are waiting for some food and it is supposed to be coming into buffet, they are making it and give it to you on your table, and then it will come to the buffet, okay, for everybody to consume. So we are trying to get it through some other channel, okay, some side track. I want you to think about it. So this is the read after write hazard. I'm not talking about the solution, but because of the pipeline, this writing is happening in the write back stage, whereas reading of the operand is happening in ID stage of the next instruction, which is 2 cycles ahead of writing. So I have to stop it if there is no other solution in the hardware. Okay, this is called true data dependency or a flow dependency. It depends on the flow of the data, or true data dependency. I want the data which is computed in the previous instruction. Okay, done. Now what is next? Okay, I will just explain this var and wow and stop. Okay, I will talk about it later tomorrow in detail, but this will give you a logical conclusion. Just give me 2 more minutes. So it's all same, 2 set of instructions coming one after the other, but one guy is having a write and read. Okay, let me come here. Just jump here. You can read it later. It's not required. Now, what is happening here? It is writing into R1 and reading is happening here. So this writing should happen after this reading is happened. Okay, that is what is called write after read. I want this writing of this R1 should happen before R1 is read. Immediately some of you might have thought it is already happening that way. In a RISC pipeline, when this instruction and this instruction are entering into the pipeline, operand reading is happening first, and then it will write the result here. But okay, there is some R3 here. I should remove R3. Sorry, I should not have R3 because there is a raw read after write is also there. I don't want to confuse you. So assume that there is some other register R5. I will change it. I remember to change. So we are only worried about R1 common. There is nothing else is common. Now, okay, let me erase it. I will explain this and stop. I think I will go to the next one later. Okay, we'll stop here. So I'm talking about reading this R1 should happen first, and then only writing into this should happen. Right after the read. That is what this instruction wants. And if you know the RISC pipeline, you know that reading is happening in the ID stage of this instruction, which has happened ahead. Then this guy will write it when it comes to the write back, which is still behind. It is going to take 5 more cycles for it to complete. In that case, there is no possibility of this hazard happening in a RISC pipeline. Okay, this is not likely to happen in a normal RISC pipeline. This hazard will not happen, but you are going to learn about out of order execution. See, even though instructions are given in this order in the memory, they are read from the memory in the same order, but execution of these instructions are not going to be following the sequence. Means taking into the pipeline itself is not followed in a dynamic out of order execution. That is a much more complex structure, which we will talk about it maybe down the line. So when such things happen, there is a possibility that this instruction will be executed first, maybe completed first, and before even this instruction started executing. Imagine a situation wherein the instructions are ordered like this, but inside the hardware CPU, we have some facility that you can execute the instruction in any order you want, okay, out of order. Then imagine a situation where this is executed first and then this instruction is even started. Then there is a problem. This instruction is completed out of order. So if T2 is smaller and T1 is larger, this instruction picking up reading R1 is larger. That means it is coming late. Whereas writing into R1 happening first, which is T2, smaller number. So, in a much ahead, you are writing it, suppose. Assume in a out of order, it is possible. In that case, what will happen? This new value which is written will be read by this, okay, which is wrong. Because program order is something to be always accepted, followed. Even if the hardware is doing it ahead and out of order, you should make sure that this correctness is maintained. If it is not, then it's a problem. So this right after read hazard happens during this kind of situation, not in the risk pipeline that we studied or we are studying. Okay. So with this, I am stopping. This is called false dependency or anti-dependency. Okay. Guys, okay, let me stop it. Record.